Bottle rockets are a great example of Bernoulli's equation in action. Here's how it works. Bernoulli's equation is essentially the conservation of energy law for fluids in motion. The pressure energy, kinetic energy, and potential energy sum to a constant value along a streamline. For a bottle rocket launch, we input the initial pressure into the system. This determines the total energy of the system because the initial velocity and elevation can be considered zero. We can rewrite this equation to find the pressure, velocity, and elevation of the fluid at some point after the launch, where the subscript 1 represents initial conditions and subscript 2 represents this future point in time. As soon as the bottle is launched, the water will start to exit through the nozzle due to the pressure inside of the bottle. Eventually, P2 will become equal to the atmospheric pressure, which is much less than the initial pressure, P1. Therefore, we know that the kinetic energy and the potential energy for most launch angles must increase to compensate for the loss in pressure energy. As the water quickly exits the bottle, it creates thrust, propelling the bottle into projectile motion, which will look something like this plot. Here's how this motion looked for one of our launches. Although many other factors come into play in a spacecraft launch, you can see here that the initial motion follows a similar trajectory.